now I have started the recording properly. I'm gonna turn, there we go, that should help a little bit with the lighting. So, last time, generic nodes, and we got decently far in the slides. Where were we? So what did we do? We got to, in our node header, this is our generic header, and then in our node CPP, we're leaving it basically empty. We're gonna include the node header, but that's it. Here, this is where we're gonna write everything. Here's, we would write our includes. Here we're saying the attribute, something of type T, but what's T? I don't know. We're gonna specify that later. But T will all be the same. If T is specified to be integers or integer pointers, all the T's, it's like basically doing a find and replace T with int star. It's basically like doing that if we wanted to do integer pointers. So here, this is the header like normal, where we explain like the what. But then below, we write all the template stuff. And it looks like we're explaining the how, which like we are, but this template code will get generated into regular stuff that you would think about writing in here. So yeah, we've got our basic constructor, and we set it equal to 0, where before, when it was an integer pointer, we made the default value like a null pointer. But because we don't know what the type of data is, data might not even be a pointer type, so we just assign it to 0 as the default value. We create another thing with the non-default constructor, one that takes something of type D and just automatically sets the data, our copy constructor, our deconstructor, and that's all we've got so far. And, in our deconstructor, we're not going to put anything here. You might say, well, what if T is like a bunch of pointers to something that was allocated in dynamic memory? Well, really, we don't need to worry about that because, again, it's that same idea of, these nodes are not responsible for creating and destroying that data. That's somewhere else's problem. That's some other chunks of code problem, not the nodes. And because none of this is like any overly sophisticated type, there's nothing dynamically allocated by this class, we don't need to delete anything. So that's where we left off. Are there any questions before going into any further? Okay, all right. You guys are so good. You're easy to teach. All right, so what should go in here? Okay. So now we've got our get data and set data. And no, if we go back here, what do we have? Well, we've got our constructors and copy constructor and deconstructor, but we only have 4 methods here. Get, set, get, set. So it's actually gonna be pretty easy, I think. So here's our gets, or here's our get for the data. Just gonna paste it in, and what do we see? Well, again, template class T. It returns something of type T, whatever that is, and node, the T there, get data. Now, I will say, by the way, whenever I start writing this code again, every year I go and I'm like, how do I write this again? Do I do that, or do I need that there? How do I? Honestly, I never remember. This is going to be something that you'll pick up with repetition. I don't really have a trick on how to remember it. My trick is have working code somewhere, and then I'll always re-reference that to be like, oh yeah, yes, I must include that. And for the copy constructor, do I need to have that there? Oh yeah, okay, there. I know this one works, so I'm happy with it. And here is our setter. So we've got our get data and set data. Get data takes nothing, and it returns something of type T, whatever that is. Our set data, it takes something of type T and assigns the attribute data to be that, but it doesn't return anything. And similarly, actually, you'll notice that if we go to our int node, our GetNext, do we have int node? Yes, we do. You'll see the GetNext is very, 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 very similar. There's nothing special with T going on except for the fact that okay, well, it's, it's returning it, we have to include that there to specify that, yes, this is the generic node, but ultimately it's just that. And the set is this. That's it. It takes a node pointer. We're good to go. This is it. This right here, though, this is what we put in the CPP file. Because, again, the template is what C++ will use to like generate the code that we would be putting in our CPP file. The code that wouldn't have like template class T. The code that wouldn't have the T. The code that would be like, okay, no, it's like integer, you know? That's what gets generated when we go to build our class. So if I go back here and we're to write something like, I guess I should include node.h. Perfect. If I were to say like, okay, I'm gonna make a new node of type int pointer, some node equals a new, oops. What am I doing wrong here? Oh. What am I doing wrong here now? Or do I not need it on the other side? Let's go have a look. Jeez, how did I forget this? My goodness. I want this to be a pointer to a node that contains pointers to integer pointers. Pointers to integers. So in this scenario, I don't have a code. There is no code. I suppose there technically is with int node, but pretend int node doesn't exist anymore. Like it's not here. Or here, if I do node char pointer equals new node of char pointer. There. There is no code in a node CPP file that like has chars in there. That's not there. But when I hit build, it's going to go and generate that code for me. It's going to go and like make it so that works. See, look, it even said, it's probably hard to see, but right here, it actually says generating code, ... So it's like building that for us. So we don't need to write it. We didn't need to write the stuff for int pointers. We didn't need to write the stuff for character pointers. We didn't need to write the stuff for character pointers. I didn't have to write that. It'll generate it for me automatically, which is awesome. So what did I miss? Okay, you said that. Yeah, so yeah, it generates the code. I already said that. So here's what I'm gonna do. I'm gonna replace this right here. There. Here we go. This is my new main. What am I gonna do? Well, let's take our time. So right here, we want a node pointer of head, but what's the type of node? Well, it's integer pointers. So we're creating that there. And I guess we're using the default one. And what are we doing? Well, we're dynamically allocating an integer 55 and we're setting head's data to that. And then we're gonna say, okay, head, get the data and then dereference it because it's an integer pointer and print it out. So I should see 55 printed out. Now here, what am I doing? Well, I'm creating a node pointer, but the type is just an integer, not an integer pointer, just an integer. Why? Because I can do it. And I called it another head and it equals a new node of int. So basically all I'm doing here different is, well, it's not integer pointers, it'll just have an integer. So when I set the data, I don't need to make a new integer. I just put in the integer I want it to store. And here I just say get the data and I don't need to dereference it because 66 is the integer, it's not a pointer to anything. And then down here, my goodness, what's going on here? I want you to take, I'm gonna zoom in. Look at this code and visualize what it is. Try to, if you have a sheet of paper and a pencil by you, great, draw it out. But if you don't, try to envision what you would draw on the sheet of paper to mean this code, lines 15 and 16. Like, what does this represent? I'll give you a second on this one because it's interesting. So I want to see what you all think. I'll give you a second because this is an interesting exercise. I'll shut up though, so you can actually think. Oh, if you're writing the answer, you're spoiling the fun for everyone. Can you explain the set data in the first one? This right here? All right, well, we'll go back to that and give everyone a chance to do to think about this, and then we'll go back to that one. If you're thinking, I'll start explaining it now. If you're thinking like, well, hold on, he's doing something weird. Like this is he's pulling some funny tricks. I am not. C++ doesn't let you pull funny tricks. C++ requires you to follow the rules you've been following since the beginning. So, node pointer. But what's the type? What's T gonna be? Well, the type is gonna be a node whose type is int. So what would that mean visually? Well, what it would mean is, imagine for a second, we already have a node that contains an integer, which we do right here, called another head. I'm going to draw that as AH. So we have AH. And AH is a pointer to a node that contains the number 66, right? And it has a pointer to, I guess here, null, because we never set it to anything, right? Now here, I'm saying, okay, create a new node pointer that's going to have, like its data is going to be of the type a node containing an integer. So this right here is a node containing an integer, right? So when I say, what did I call this one? A. When I said A, you're a new node, so you're a node, and what you contain is a node of type integer. Now notice this, I could have done this, where the data would be a pointer to a node containing an integer, but I didn't. So if I did put the star, data, so up here data is 66. If it was a star, it would be this, but it's not a star. So really what I did was I kind of made it so, I'm gonna have to like redraw this. Let me go back. Oh, I guess I can't go back anymore. No. I don't know what I did. So I may have, did I ruin? Can you all still hear me? Uh-oh. All right, I think I angered my computer. Okay, you can still hear me. I think I angered my computer by doing too many undos in Microsoft Paint, which apparently will kill Microsoft Paint. Let that be a warning to all of you. Microsoft Paint will destroy your computer. Apparently. God, I can't even open my task manager. All right, let's see. Where's Microsoft? Oh, here we go. I'm gonna kill you. Okay, let's try again. All right, so I have AH, which is a pointer to a node where its data is 66, okay? But then I made A, which is a pointer to a node whose data was this. So this is pointing to like null, and I guess this is also pointing to null, to nothing. Now, if you're thinking like, wait, what? That's really weird. Why would you do this? Was a weird thing. Now, don't get me wrong. You would, there are totally reasonable situations where you might want to do something like this, but do understand that this is a particularly funny situation. I also probably would have at least made node, the types, I would have probably have done this, and then I don't have to dereference anymore. Oh, what did I do wrong? It's got to be a node. Oh, right, and this has to be the pointer. I would probably want to do it this way, where I probably have to wrap that in parentheses, where I would at least have made node, the T be a pointer to a node that contains an integer. But anyways. what was the question? Can you think of an example where one might use this? Yeah, I mean, it's kind of similar to the idea of having like arrays of arrays, really. Here you can have like nodes of nodes. So like imagine you wanted to represent like a 2D matrix with an array. Well, that's easy. You have like arrays of arrays, right? That's not crazy. We've done stuff like that before, right? But imagine you want to represent a 2D matrix, but instead of having like arrays of arrays, what if you want it to be like nodes of nodes? So that there is an example of it. It's not really a contrived example, but perhaps a lazy example. But there are other reasons why you might want to do it. And that's a possible one. I know it seems like, well, that's weird. You would never do that. But once you start doing it and you realize that there might be some interesting value to doing this, you end up using these ideas weirdly more and more and more. The point of all this, though, is this right here, what I did here, here, I'm going to undo all this nonsense. This right here, I wasn't pulling anything weird or fancy. I was just following all the rules. The things in the triangle brackets are the type. Well, what's the things in this triangle bracket? Well, it's a node of the type, int. So there you go. I've just nested them inside. Now, there was a question about this, and in this scenario, perhaps this will make it slightly more obvious. There. And then here I can do like some, there. Does this help to the question that was asked earlier? Yeah, there you go. It's just, I was being fancy and doing it all in one line, but all I did was create an integer pointer of some integer declared somewhere in dynamic space, and then I just gave that pointer to here, so it copies over the value inside this variable, which is a pointer to that integer. But I was being fancy and I just did it all in one shot like that. I will say, and I've said this before in 161, but there's always value in repetition. And for those of you that have come not from 161, a lot of new programmers will think like, less lines of code, that's better. No, that's probably not true in general. Oh, wait, if you had toString method for the node, would you? Okay, I'm gonna come back to that. So new ints make a pointer to it. Well, no, hold on. New ints. If I wanted to just make an int, that's an integer a, but this isn't like static memory, right? The computer's like, okay, yeah, I'm just gonna go find a chunk, put 55 in it, there, I'm happy. And I could do something like this, wherever the ampersand key is. There we go, hey, like that works, oops, right? But when I say something like new int, what this does is it says, okay, go to dynamic space, create an integer with the value 55, and once this is done, this chunk of code here returns, kind of like a function returns. It returns the memory address of where C++ decided to put this in RAM. That way, when I do something like this, where int pointer b, like b is a variable that must hold a pointer to an integer. And this variable b is in static memory. This here goes and creates the integer 55 somewhere else in dynamic RAM. And then once it's done being created, C++ comes back and says, okay, I made it, and it's at memory address 5,000,000,002. And then because this right here, 5,000,002 is a pointer to an integer, well, we can shove that memory address into b. That's all. Think you're making the classic mistake. So new int makes a pointer to it. It makes the integer and returns the pointer to that integer. Maybe that's what you meant, but I'm just being overly precise with my wording. Now, I will come back to Cole's question in 1 second. What was I saying? Right, about lines of code. We're soon going to learn about like efficient code. Now, the only value really of doing it in one line of code like this instead of having what I had a moment ago where I did like, let me keep going back. Hopefully this doesn't crash my computer. There we go. There. The only value of having it instead of this is like, sure, it saves me a line of code. and some characters, which then the file size would be smaller because it used less characters, right? But I mean, it's such an inconsequential amount of space that, like, on these computers, not gonna matter. If you're working on some hilariously small embedded system, okay, there might be an argument there. But this right here is not more efficient code at all. Soon, in a lecture coming up very soon, lecture 13, we will be talking about, like, well, what makes one algorithm better than another in terms of computational complexity. So we are going to get there. But having it one line is not better. It's not worse, it's just not better. In fact, one could make an argument, as it was just brought up, there. One could make an argument that this is better code because it's more self-descriptive, you know? You look at this, and it's very clear, oh, I'm making an integer, oh, and then I'm signing it. You know, like these 2 lines of code, it's more verbose, but with that more verboseness, it's more descriptive. It describes itself. You might look at this and it might be more obvious, like, of what's happening, what's going on, versus the alternative. So sometimes more lines of code is better if it becomes easier to understand. But of course, as a good programmer, I always comment, right? So let's see. If you had a toString method for the node, you wouldn't always be able to convert a node to a string in the same way depending on the type you just made. For example, if you made the type of the node int node. So you are correct. And this is where we run into a problem with a language like C++, where languages like Python and Java were able to learn from C++ and improve upon it and eliminate this issue. So as soon as we throw in generics, you're absolutely right. We run into a problem where, well, hold on, how can I guarantee that the thing of type T has, like, I can call toString on the thing of type T. How can I guarantee that? And you can't. You cannot guarantee that. But here's a little lesson in other object-oriented programming languages. If this was Python, if this was Java, let's talk about Java, because I know a bunch of people here have some Java experience, and Java is perhaps a little closer to C++ than Python is. But the same that I'm about to say is also true for Python, except instead of toString, it's repr. So, 1, there's primitive types and objects, right? In Java, if you want to do your generics, you are only allowed to do generics of objects. There's no such thing as a generic of type int, or a generic of type double, or a generic of type bool, or character, or something. You can't do that. That's against the rules. However, for every primitive type in Java, there's an object version of that type. So if I wanted my thing to have a generic with integers, I would use the object version of the primitive type. It's effectively exactly the same. No, it's going to act very, very similar, like in practice of like using the integer to do integer type things, but it is the object version. And literally, if this is Java, so if this was Java and you did this, it would be unhappy, right? But you would do node this. If you spell out integer with the uppercase, that means the object version of int. Or instead of double, you would write double, and that's the object version of double. So all objects in Java inherit, and we are going to talk a little bit about inheritance very soon, right here, slide set 16. In Java, everything inherits from this one super duper ultra uber class called like the object class. Everything is derived from the object class, and the object class has a very special function that exists inside of it. It has a couple of special functions, methods perhaps I should be saying. It's got a couple special methods. One of them is something like equals, okay? There's something like your dot equals method that will tell that you get that for free, and it checks if 2 objects are the same. you've got the toString. There is a toString method inside the object class that will convert your object to a string. But the equals that you get that's written in the object class in Java, all it will ever do is tell you if the object is the exact same object in memory. Like imagine you had two pointers that pointed to the same object. It'll just tell you, is that the case? And that's what you get for free. And the toString in Java basically returns like the class name and the memory address of where like it is. Okay, so it's just a bunch of like garbage. Like it tells you the memory address of where the object is in RAM, but that's not going to be overly valuable, right? Like if you've got a student object, you're going to want your student object to print out like, okay, your first name, your last name, and your email address or something. Not like student OXA712477112272. Like what good is that, right? So what we do is we override that method. So by default, every object we ever create automatically inherits from type object. That means for free, whether we write them or not, we get methods like your equals and your toString. So those functions must exist. But when you come and create your own class, like a student object or a course object or a node object, you should be overriding the toString to make sense for what your object is. So, because all objects inherit from the superclass object, they get that object, every single object you ever write, whether you override it or not, has a toString. So you are guaranteed that because your generics, they must be of things of that are objects, and every object has a toString, whether you like it or not, you can always, always, always safely call toString on an arbitrary type T. But in C++, there's no guarantee that the thing of type T has a toString written. Just as you brought up, Cole, where like if I say like toString on an int, but if I want the string version of an int, I should be calling like the standard library's toString. So suddenly that's just completely broken. Where Java and Python, and by the way, everything I said about Java is true for Python just with the repr version, but everything in Python's an object, so you don't need to worry about primitive types versus non-primitive types. So couldn't you detect the type T, what type T is, and write a toString for every type? Well, here's the problem. Like, ints, you would have to go back and open up the code for what an integer means inside C++ and then go write your toString. So that won't work because you can't guarantee that I didn't make something of type int. And I don't know about you, I don't see no int class here, right? Like I don't see the code, like an integer, there's like, we can't write a toString for an integer. That's not a thing. So that's why we're really in big trouble here. So long story short, Cole brought up a huge issue with toString in C++. Other programming languages were able to learn from this and come up with clever solutions to fix it. But as you have seen, and as you will continue to see, C++, I like to think of it as a giant burning pile of garbage that people keep stapling things to and say like, no, everything's fine. This is good. We like this. And there we go. Where other languages look at that burning pile of garbage and go, well, that part's okay, but maybe if we do this instead, it won't spontaneously combust or something. Joking aside, C++ is great. There's a lot of value in C++, but this is one of the shortcomings. So by the way, Cole, exceptionally observant and astute observation. Very well done. Very, very, very well done. In fact, we will be talking, like that's in some slides coming up. I think probably the next set of slides. So very well done. Very impressed. Any other questions about generics before we jump on to stacks again? What is the next set of slides anyways? Sure, save. Linked stacks. Okie dokie. So no other questions, eh? Like that makes sense because you'll probably have more questions the more we use these things. So that is a-okay. All right, linked stack. But we already learned about stacks, I know. But we implemented the stack with arrays, right? But we learned about linked structures, where we have nodes that have data and point to other nodes that have data that can point to other nodes that have data that can point to other nodes, and so on and so on and so on and so on. Can we build a stack with linked things? And the answer is yes, absolutely. So we're going to do that. Pardon me. We're going to do that, and we're going to make it generic. So the point of this lecture is to use link structures to make a stack and make the link structure generic and see how to interface, or see how like the interface and the implementation are very separate ideas. I know I was emphasizing this before. Now it should become more obvious what I mean when I say the what, the interface, and the how are, we want these ideas to be like separate. This is what we want our stack to do. Nothing of what we see here tells us how it has to be done. We know that push, well, that's to put something onto the top of the stack. Pop, that's getting something off the top of the stack. Peek is empty, size, toString. None of this says, oh, but use an array. Use a link structure. Here's how you got to code it. None of this is in here. All it does is say what it can do. So that's just a bunch of operations that just says what can be done, and it says nothing about the implementation, nothing about where the data is stored, nothing about how the operators do what they do. These ideas also have nothing to do with C++ or Java or Python. These ideas are programming language independent. Hell, they have nothing to do with the programming language. I could tell you to go do these operations with a stack of blocks like a child would. And if I say push something, you go, okay, I'll just put it on top. Pop something, okay, take it off. You can do these operations yourself. Nothing to do with code at all. This is an important feature. And this right here is something that takes people a long time to get. And usually it's because professors do a bad job at emphasizing this difference. But this is, it's important to note the difference. Yeah. So this is the definition of the abstract data type. It's a collection of data and the operators we use on the collection of data. Okay, so we need a thing that will hold on to the stack, the container. And we're going to use the link structure. Last time we used an array, we can use the link structure. And we also need to keep track of the top of the stack. Remember, that's what we did with the array implementation. We had our array, and then we used an integer to keep track of like the top. Really, the top was the next available spot. That's the scheme we used. But it was just an integer that told us where in the array the top is. So we also need a thing to keep track of how many things are in the stack. Now, with the array, top played double duty, right? It kept track of the next available spot and also how many things were in the array. But here, we're gonna have to figure out how to take these ideas and make it work with the link structure. So let's do it. We're gonna use a series of nodes, obviously. If we use the generic nodes, we can make the whole stack generic. Awesome, we like this. And here's the idea. What we'll do is imagine I have some stack right here. Some stack is this. So this is like I wrote something like stack of type squares equals new. Oh wait, there should be some. I already blew this. Let's see if I can undo. I did the squares because that's what these are. S equals new stack type squares and then parentheses. There, that's like what I did here. This is what we want to achieve. I realize you're going like, wait, hold on. We never wrote the code for this like link stack. I know, but this is like the idea of what we're ultimately getting. This object is going to have two attributes, it looks like. Top, which is a pointer to a node. And top is always going to be pointing to the head of the node, which is also going to be the top of our stack. So it looks like all the inserting and removing is going to take place at the beginning of our linked structure, which is good. And then we also have a count variable. That's just going to keep track of how many things we have in our stack. If we push something new on, well, we're just going to like insert at the front of this linked structure. And if we're going to pop something, we remove from the front. And if you remember from the last set of slides, inserting and removing from the front of the stack isn't too bad. It's not too complex. Yeah, after popping another unlinked, great, cool. So where does all the action happen here? Okay, at the front of the link structure. Pushes and pops, yeah. Which type of insertion deletions do we need? Well, I already spoiled this one. Insert at the beginning, delete from the beginning. So top will be a pointer to the head of our link structure. It will point to a generic node of whatever type, and count will just be some integer representing the number of things currently in or on our stack. So here's what we're going to do. Let's start implementing our array int stack. Now, we already have our array int stack. This is what we had. Pardon me. This is what we needed. We had our max, top, our pointer, an integer pointer, or an array of integer pointers, and void, expand capacity, and then our constructors, push, pop, peek, size is empty, toString. So what are we going to want to do if we have a link stack? Well, we're going to want to include our node.h because we already wrote our generic node. Template class T. Why template? Well, we want this to be generic. So you'll also see that we can have like generics cascade down. So here's what I mean. This class here that we're writing, this template, is going to be of some type T. If I want it to be integer pointers, so I want a stack for integer pointers, T becomes int star. But then what is the data that our node needs to hold? Int star. So we can like pass the fact that this is generic all the way down as far as we need. We'll just pass the T on to creating a node of some generic type as well. So what do we have? Our attributes. So we've got our pointer to the node, the top, and int count. I'm being bad here. I should probably have the underscore in front of count. I've got my constructor, my copy constructor, and my deconstructor. No, I don't have another constructor here because I don't even really know what that would be. So I'll just leave it like this. I've got my push something of type T, pop, peek, size is empty, and toString. But toString, as Cole brought up, could end up being a little problematic. So linked stack, okay. Well, generic, this is all we're gonna have. I'm gonna go here and start. So let's go, okay, right click, add, class, linked stack. It's going to create the header and the CPP file for me. Fantastic. So here's the header. Here's the CPP file. I'm done the CPP file. That was easy. So here we go. Well, oops, that's not right. Perfect. We're in good shape. I'm going to go back and copy all this. Look at that, typo. Perfect. So here we go. Template class T, yeah. All right, cool. So our header is all set. But of course it's not because we need to now write all the template stuff. Okay. So this is done. Okay, so now it's generic. Remember, we're making it generic, so we write all the code in the header file. So here's our constructor for linked stack of type T. You'll notice here that node here, its top is going to be a pointer to a node. Remember, I like pointers. So I'm allowed to do null pointer for top because top, it's going to be like the type of top is going to be a pointer to a node of some generic type. Now, the data inside the node, like right here, may not be a pointer, but the way I've written it here, I know that this must be a pointer to a node. So that's why I'm allowed to do top being a null pointer and count to 0. There's currently nothing on the stack or in the stack. So there's our constructor. our copy constructor. Now this is hairy. Let's have a look at what's going on here. And I suppose in this scenario, we actually have a decision to make. The decision we have to make is, how deep do we want this copy? Do I want the copy to be as deep as possible, that if there's something of type T, I go down and copy those over, but I don't know. Do I need to copy them over? Because I don't know what the types they are. Are they going to be in dynamic memory? I don't know. But here's what I do know. I'm probably going to want something like this. If I have some stack, that is a pointer to some object that's got top, which is a pointer to some node, which maybe it's a pointer to a square, okay? Which also has a pointer to some other node, which has a pointer to another square. And then this is a node that is a pointer to another square. And then this just points to null. If I want to make a copy of S, I probably don't want it to have something like, I don't know, Q point to the same object. Like that's dumb. That's obviously not right. But do I want something like this where it's like Q is a copy of the stack where underscore T, do I want it to be pointing to this? So the stack will actually be pointing to the same nodes that contain this. You know what? That probably doesn't make any sense. If I want a new stack, because remember with the array stack, I made a new array, but I copied the pointers over in the int array stack. So what I think I'm going to want at the very least is to make a copy of this node, which contains a pointer to that same thing. We have a decision to make here. Does it make sense in our case to have it point to the same thing? Well, this is a decision we have to make. And in our case, I think it makes a lot of sense to have it point to the same thing, because if I have a copy of the stack, like if I really want it to be a copy of those things, of these boxes, these squares, I could code it, and I could write code in like my main, for example, to create a new stack and just copy everything over. But I think I want my default copy to just be copying over like the structure here, but then just copy over whatever the contents of this is. Because these might not be pointers. These might be actual like integers. And if I want a copy of this, I would just copy over the fact that there's a 1 in there, which there isn't, because here I've got pointers to squares. Anyways, that may be confusing. Let's not worry too much about it right now. Point is, because I don't know what the data is in here, I don't know what T is, like the generic T. If T was a boring old integer, here it's pointers to squares. So I'll just copy over whatever data is, which is a pointer to this square. But if data happened to be a primitive type, like the number 12, I would just want to copy over 12 into here. Anyways. So, okay. The first thing we're going to do is copy over count. If the stack we're copying is empty, if count's 0, then there's nothing in the stack. So top should be null. It should be null pointer. Okay. But if it's not empty, we're going to have to start copying over those nodes. So what are we going to do? Now, this might seem hairy, but we're going to go through it, and then I think I'm going to do it in Paint if we have time. So we've got a node pointer T called newCur, creating a new node, and I'm copying over the top, whatever like the thing top points to from the other object. So I make a copy of it, and then I set that to top. So top is now pointing to what newCur was. So if we go back here, if I have S, oh man, for top, okay. What am I saying to do? So I say newCur is a copy of that one. So I've got my new thing here. And I say, okay, so this has newCur, NC, and it's going to point to a copy of this. Okay, so I'm going to make a copy of this. and that's going to point to that. Then I say, okay, top, you're equal to new cur. Okay, so top, you're going to be equal to whatever this is, and this is just a pointer to this node. So, boop, great. And because we're just calling right here, this right here, this calls the copy constructor for the node. And let's go look at the copy constructor for the node. That just copies over whatever the data is and the next is. So we already know how to copy a node because we wrote that code right here with this copy constructor. Yeah. Now here, I've got old cur is going to point to top. Okay. So now I have old cur, OC, point to here. So now I have three things pointing to top. So what the heck's going on here? Ah. So now what? Okay, so I say, well, old cur's next is not null. Okay, so if old cur's next is not null, so here, let me draw this here. Remember, when I made a copy of this on line, right here, line 47, when I made a copy of new cur, or of the, sorry, the one we're making a copy of's top, I copied everything over. So I missed something very important here. I copied over whatever the data was, and I copied over whatever the next was. But what is next? Next happens to point to that at this stage. So when I ask the question, hey, old cur, is your next not null? It's going to say, okay, old cur right here, is your next not null? And of course, that's true. So what are we going to do? We're going to say, okay, new cur, set next to a new node of the old cur's next. That is one heck of a line that says, okay, new cur, don't point there anymore, point to a new node. Oop, no, I skipped something. Ignore that. There we go. Okay, new cur, your next. So this guy, your next now, is going to be equal to a copy of old cur's next. What's old cur's next? Well, I mean, that's still here because we haven't updated it yet. We're about to update it. I'm going to say make a copy of this guy. So we make a copy. Ooh, copy. Boom, and that will point to whatever's next here. This doesn't point here anymore because we just said new cur, you're there. And then what do? We say new cur equals new cur GetNext and old cur GetNext. I'm not sure that there's necessarily a necessity for old cur and new cur, but anyways, new cur. And then old cur. And so on and so on. So this will go all the way down until old cur's next. Imagine this was null. Then we would stop here because we now know we're done. I will revisit this on Tuesday because we are out of time. Hopefully you enjoyed it. Otherwise, I will see everyone on Tuesday and half of everybody in an hour at lab. So enjoy, enjoy, enjoy.